In this lecture we will consider the reliability of wind turbines. Operations and maintenance costs for wind turbines are a significant fraction of the levelized cost of wind energy. For turbines onshore, this fraction is around 15%, but offshore this fraction can easily be doubled. The reason for this is mainly due to the logistics of access. The average wind speeds offshore are higher than onshore, and access is primarily by boat. Maintenance vessels can only operate in a limited range of wind and wave conditions. This means that particularly in winter, access can be very limited. The cost of chartering a vessel large enough to transport spare parts to an offshore wind farm is very high. This can cause the costs to mount up if the sailing of a vessel is delayed due to adverse weather conditions. To understand some of the challenges of offshore wind turbine maintenance, we first take a look at the reliability of wind turbine components and sub-assemblies. So, let's inspect a wind turbine rotor and nacelle. The rotor normally consists of 3 blades made primarily of composite material. It converts the force of the wind into a turning moment. The blades are subject to significant fatigue due to the ever-changing turbulent nature of the wind. Defects in construction or damage can lead to crack development or delamination of joints at the trailing edge of the blade, for example. Erosion by particulates in the air can cause pitting and loss of aerodynamic efficiency. The blades are connected to a hub and normally have a pitch mechanism to control the amount of power extracted from the wind. As the wind is ever varying, these actuators see a significant amount of service during the turbine's lifetime. Pitch bearings can get worn, motors can fail, or hydraulic fluid can leak. All of these compromise turbine performance as well as safety and require maintenance. To keep the rotor aligned with the wind, electrical motors or yaw drives are required to rotate the nacelle. These do not operate as frequently as the pitch motors, but nonetheless need to withstand large loads as they move the nacelle around in a turbulent wind. This loading can cause wear to the yaw motor or the yaw mechanism, which usually has a small gearbox. Excessive movements can contribute to premature failure. The hub is connected to a large main speed shaft with a very large bearing that must withstand a large inline thrust load. During operation, this bearing also has to withstand significant off-axis loads which contribute to wear and possibly failure if these loads are excessive. The main shaft is often connected to a gearbox to step up the low-speed rotation to a high-speed rotation required by a traditional generator. Here you have a large mechanical component which is in service under variable loading conditions for most of its life. Compare that with the gearbox of a car which is idle in the garage for most of its life, and you begin to understand the conditions that a turbine must withstand over its 25-year lifespan. A gearbox needs to be properly designed to withstand in-line and off-axis forces. If it is not properly aligned, then adverse wear can occur, which can result in premature failure. Lubrication is an important factor and must be efficiently maintained throughout operation. The generator is a key component as it converts the torque into electrical power. The manufacturing tolerances required to maintain the very small air gap between the rotor and stator is small, but necessary for maximum efficiency. Such small tolerances mean that any eccentricities in the generator shaft can result in excess bearing wear or even rubbing between fixed and rotating components. There is also the added complication of electrical windings which can get hot, leading to possible damage if cooling fails. Let's have a look at the statistics. A number of studies have been performed over the last decade to try and quantify the reliability of wind turbine components. It can be difficult to compare one study with another, as different studies have looked at different types of turbine technologies with different ages and locations. Nonetheless, we can draw some general conclusions. Let's look at one of the earlier studies of a large number of German onshore wind turbines. Although this study was for an onshore fleet, similar trends have been seen offshore. The figure shows failure rate in blue to the left side of the bar chart and downtime per failure in pink on the right-hand side. 2 different fleets of turbines were studied, which is reflected in the light and dark colours. If we look at what fails most frequently, it can be seen that this is the electrical systems and control. On the other hand, if we look at what contributes most to the downtime, we see that this is the large mechanical or electromechanical components such as the gearbox, the generator, or the drivetrain, for example the main shaft. This can be explained if we look a little more closely. Electrical failures are often relatively trivial problems like interruptions and variations in the grid connection which cause a turbine to shut down. These happen relatively frequently but can be reset quite quickly, often remotely. On the other hand, if a bearing fails in a gearbox, then this requires a major intervention. Indeed, if the gearbox needs replacing, this will require the delivery of a new gearbox and the use of a large crane to remove the old gearbox and install a new one. This can be a time-consuming and also expensive process. Looking at the associated costs, the replacement of a gearbox is by far the most expensive single maintenance operation, as can be seen in the next figure. However, if a developing fault can be detected at an early stage and a minor repair can be performed to avoid failure, maintenance costs can be significantly reduced. This is where condition-based maintenance becomes important. Looking to the future, for condition-based maintenance to make a real impact on reducing the costs of operations and maintenance, we face a number of challenges. Firstly, embedded sensor technology needs to be developed to give real insights into component failures, for example in bearings. Secondly, the large quantity of data produced by the different monitoring systems on the wind turbine needs to be managed and standardized to allow for monitoring across a range of turbine types. Thirdly, more sophisticated algorithms need to be devised in order to detect and diagnose problems at an early stage. These algorithms should combine the attributes of a data-driven approach, making use of machine learning, with the ability to model the physical mechanisms which underpin the various component failure modes. Condition-based maintenance systems should then be able to predict timescales to failure with a sufficient accuracy to make informed maintenance decisions. Finally, the information provided by such systems should be appropriate for a range of stakeholders, from the technicians who need to go out to the wind farms, to the managers of large fleets of wind turbines who need to ensure high levels of performance through cost-effective decision-making.